Good afternoon, good morning, good evening. So I'll be talking about our recent work, which is there in the archive and which will also appear at the ITW workshop shortly. So it's a great privilege to be talking at Beyond IIT. So the title is One Shot Inner Bounds for Sending Private Classical Information over a Quantum Multiple Access Channel. Joint work with my student Sayantan Chakraborty and Aditya Nema, former student, but now he's a postdoc at Nagoya University. Okay, so the problem here is as follows. So there's a channel with input Alice, okay, and output Bob, but the channel also has another output called the eavesdropper, which we are calling Eve out here. So the idea is Alice would like to send some message from her end to Bob's end. Bob is a legitimate receiver, but because of the characteristics of the channel, whatever she inputs to the channel, some information about it, as modeled by this output wire, goes to Eve. Okay. Now, normally think of the information that Eve gets about the input should be less than the information Bob would get. Otherwise, the channel is useless for purposes. So, what is our purpose? The purpose is, can Alice send messages to Bob while hiding them from Eve? Okay. It's a noisy channel, so one has to do some encoding and some decoding. But unlike the usual point-to-point channel, this channel, which is called the wiretap channel, requires a secrecy condition, okay? Namely that whatever Alice's message is, so Alice will encode it into a code word, input it to the channel. Bob should be able to decode from the channel output, and Eve should have almost no information about the actual message M that is sent. So the same thing in some more detail. So M is the message, okay? Then let's look at the classical version to get the intuition. So it goes to an encoder. So the output of the encoder is a symbol from the input alphabet of the channel. So the input alphabet is calligraphic X, and M is encoded into a code word which will denote as XM. The channel is described by this probability transition matrix. So for input symbol X, the output of the channel, okay, is given by this probability distribution, this conditional probability distribution, where Y denotes the legitimate output of the channel, and Eve is the noisy eavesdropping information. Okay. So E goes to Eve, and Eve is all powerful. She can do whatever she wants with E. The legitimate output of the channel Y goes to Bob, who has a classical decoder, and he should get ideally M. Maybe he gets a corrupted version of M, but what we want is the output of Bob here should be equal to the input with high probability, and Eve, the message, the symbol that Eve sees, E, or rather the probability distribution of E should be almost independent of M. Okay. Now let's make things quantum. So the message continues to be classical. So this is private classical information. Now, for the purpose of understanding the protocol, it pays to split the decoding step into two parts. Okay. I mean, ideally, I would like to say that I'm encoding the classical message M into a quantum state, which I'll call rho M. But it helps to split the encoding into two parts: a purely classical encoding, where M is encoded into a code word XM. Okay. And then there's a quantum encoding, okay, which sends the symbol X to a density matrix rho sub X. So the input Hilbert space of the channel is A, and this encoding from little x to rho subscript X, okay, is this classical to quantum encoding. So this is what we get when M is inputted. Now, here is the output of the channel, okay. So this is the legitimate. So this is the. What is happening? Am I audible? Hello. Am I audible?
Yes, we can hear you.
Oh, okay. Yeah, okay. So I'm using a different audio device. Okay. So
yes, all good. We can hear
yeah,
you clearly.
so somehow I think my Bluetooth switched off, but the computer speakers have taken over. Okay. So here is the legitimate output of the channel, which goes to Bob, which I'm denoting as N, the channel superoperator N applied to rho. And there's also the Eve's output. In general, this output is an entangled state across the registers B and E. So Eve receives the register E, she can do whatever she wants with it. The register B goes to Bob, who does this quantum to classical decoder and gets a guess M hat of the message M. So again, we want that the guess M hat should equal M with high probability. Okay, and Eve should have no information about M from her input register. Yeah, so formally, we have this quantum channel from the input Hilbert space A to the output Hilbert space B and the eavesdropping Hilbert space E. Okay. And the question is, does there exist a classical to quantum encoding map, okay, which goes from the set of all messages to the input Hilbert space? Then it'll go through the channel, followed by the classical decoding map. So which will map a state in the Bob's Hilbert space B to a classical symbol in the message space, okay, such that the following conditions are met. So the reliability one is the usual one. So for all input messages, Bob should be able to recover what was transmitted with probability of error at most epsilon. Okay, think of epsilon as a small constant. There's a privacy requirement justifying the name wiretap. So for all messages M, the state on Eve system E should be close to a constant density matrix independent of M. Okay, so the reliability requirement is the usual requirement. The additional requirement here is privacy. So the wiretap channel, the point-to-point wiretap channel, which we just saw, has been studied in earlier work. In today's work, we are going to look at an extension. So we call this a classical quantum wiretap multiple access channel. So the good old multiple access channel is as follows. So here's the channel, but it has two inputs. Two senders, Alice and Bob. So they each have independent messages M and N, which they would like to send. So the output of the channel is the legitimate receiver Charlie. But because we are in the wiretap setting, there is also another output, which is the eavesdropper's side information E. Okay. So the channel now goes from AB to CE. And the aim is as before. So here is the message M. It will go through some encoding phase. It's more useful for our later purposes to split the encoding into a purely classical part and a classical to quantum part. Anyway, at the end of this encoding process, the message M is encoded into a density matrix in the Hilbert space A. Then there's an independent message N, which gets encoded into density matrix in the Hilbert space B. Okay. So remember, N is the message, Yn is the classical code word, and this is the result of the CQ encoding, classical to quantum encoding. Remember these two code words, quantum code words are in tensor product simply because the messages are independent and the encoding steps are independent. Now the channel acts on whatever the input Hilbert space contains, okay, AB. The output in general is an entangled output. Okay. It's entangled across the registers C and E. So Charlie applies his quantum to classical decoder and gets a guess M hat, comma N hat, and we require that his guess should agree with the tuple M, comma N, except with probability at most epsilon. Okay. So we want M to be the output M hat here to be equal to the input M, as well as the output N to be N hat to be equal to the input N. Okay. If even one of them does not agree, we'll declare an error, and it has to be subsumed within that epsilon probability. And again, for every input message pair M, comma N, the state of Eve out here, the Eve's register, should be almost independent. Okay. So here is the strategy. Okay. So here is the standard strategy for the point-to-point wiretap channel. Okay, and we'll just extend it to the multiple access channel. So the strategy was, remember Alice has to send the message M, so she creates a random code book. And recall maybe here that we are splitting the encoding into two parts. There's a classical to classical encoding followed by classical to quantum encoding. So the classical to classical encoding is as follows. So cook up another set X. Okay, so this is the classical code word space X. And Alice creates a random code book for each index M, comma K. So M, we know what it is. M is the message. So what is K? K is some additional randomness. So think of it like the secret key, kind of like a secret key. Okay. So K is independent of the message M. And how are these code words generated? So each code word X, M, comma K is sampled IID from a fixed distribution PX. So this distribution PX is on this classical code word space. So choose your favorite code word, classical code word alphabet X. Choose your favorite distribution PX on it. Okay. Choose a certain amount of secret key K. And then for every tuple M, comma K, I will sample the symbol X IID from PX. Now, for the classical to quantum encoding, I fix an arbitrary map from input symbols X to density matrices rho sub X. And then we'll be optimizing our encoding. So this is reminiscent of what we do even in the good old point to point. And I mean, and this is something that we all know, like because we're allowed to optimize over these encodings, additivity of whole level information fails for the very basic point to point channel. Okay. So this statement just means that we have fixed a mapping from X to rho sub X. Now, what does Alice treat the code book as? So she thinks of the code book as being divided into blocks of size 2 to the K. So 2 to the K is the amount of the secret key space, okay? And 2 to the M is the amount of the message space. So the total number of code words that are chosen is 2 to the power M plus K, okay, the product of these two sets, but they're broken up into blocks. Okay. So each block is of size 2 to the K, and the number of blocks is 2 to the M. Now to send the message little m, Alice goes to the mth block. She chooses randomly an index k in the mth block and sends the corresponding code word. So this is the classical to classical encoding, and then the classical to quantum encoding will be, she will replace xmk by the quantum state rho sub xmk, and this will be inputted to the channel out. So though I'm showing this figure for the Mac, exactly the same procedure which was done for the wiretap is done for the Mac, at least as far as the encoding is concerned. And a similar thing is done from Bob's end. Okay, so choose your favorite code word alphabet Y here, choose your favorite distribution PY on that, and then create a code book as follows as before, and then go through this procedure, the same procedure. Okay, so why is this good? Okay, so random code book is something which we all know. So we can sort of believe that this will guarantee reliability if the number of code words is not so much. But what about the privacy from it? So this is where this block business plays a role. The fact that Alice has randomly chosen an index. Okay, so she wants to send the message M, but she does not put in a fixed code word for M. She randomly chooses an index K from the mth block and sends the code word from that. So this randomization within the block should hopefully obfuscate the register E of Eve. So to send the message M, it's not a fixed code word, but rather a uniform code word from a certain block. What we hope is that just randomizing over the little block will obfuscate Eve out. Okay. But because the output at Charlie's end is less noisy, we would like to believe that Charlie still has enough information to decode at least the message M. So that's the idea. So we are done for the point-to-point wiretap, I mean, except for the analysis. So what is the analysis? The reliability, the existence of a decoder at Charlie's end is guaranteed by the usual Holebo-Schumacher-Westmoreland theorem, okay, in the asymptotic IID regime. So all we require is the total number of code words, so including the message and the secret key. So this should be M times K, I believe. So well, I think this is talking of the message length. So this is log M plus log K should be less than the mutual information. So here the mutual information is measured with between the classical code word space X and the output of the channel out here. Okay. So the total number of code words. Okay. So the total number of bits required to represent the code words. So there will be log m plus log k should be less than this mutual information. And if you want to do it in the one-shot regime, I mean, we can do it by various ways. We can do it by sequential decoding, Hayashi Nagaoka, and all. We just have to replace the mutual information by the correct entropy quantity. So the smooth hypothesis testing mutual information. So log n plus log k should be less than the smooth hypothesis testing mutual information. So that part is done. Reliability is easy. So what is privacy? So privacy is guaranteed by what we would like to call the covering lemma. So there have been various covering lemmas proved in the beyond IID literature, but the form of the covering lemma that we would like to use is this. Okay. So remember, to send the message M, Alice is randomizing over the mth block. Okay. So observe that M is fixed here, and then we are randomizing over the secret key K. So basically, this is randomizing over the mth block. The size of the block, recall, was 2 to the K. And now, like it goes to the classical to quantum encoding, the channel operation, and then finally we look at the registered Eve's end. So what we want is that the Eve state averaged over the block should be close to some fixed state. And it turns out that if the size of the block is good enough, so if log k is larger than the mutual information between, again, between the input code word alphabet X and Eve's register E. So if the block size is larger than the mutual information between X and E in the asymptotic IID regime, this is good enough. So the random codebook construction followed by this averaging over the block will give me a state which is close to, in fact, the marginal on E. And for the one-shot regime, we have to replace again the Shannon mutual information by the correct one-shot quantity. So it is the smooth max mutual information. Okay. So note that here we have the hypothesis testing information because this is reliability. So the privacy is a covering type of problem. So we get the other end of the Renyi mutual information spectrum, which is I epsilon max. So there are various ways to prove a statement like this. So our favorite way to prove this is using the convex split lemma of Anurag Anshu, Rahul Jain, and Vamsi Krishna. And it is this convex split viewpoint which we leverage for our MAC problem. So now, how do we use these tools and do additional work to do this for the multiple access channel, the wiretap line? So for reliability, okay. So if you're doing the asymptotic IID, then we can do the successive cancellation. So let's let's look at this. Okay. So we know that the achievability for, I mean, forget the privacy requirement. If it was just the good old MAC, just the reliability condition, then our favorite description of the MAC rate region is this pentagon. So successive cancellation just prescribes that we should achieve, we should design a strategy to achieve this corner point. We should design another strategy to achieve this corner point, and then do time sharing to get any intermediate point on this dominant phase. And once we get any point here, we can get all the inside points by resource wasting. So the technical tools to do this are called successive cancellation. All that it means is that, let us say if I want to achieve this corner point, then the prescription is Charlie will decode for Bob first, treating Alice as noise. Okay. And then she will decode for Alice using our output and Bob's decoded message as side information. So this ability to treat Bob's decoded message as side information is what is formalized in the literature as successive cancellation. Then time sharing is there. But in the one-shot case, we would, I mean, there is no time sharing, so we would like to use a simultaneous decoder. So we'll use a simultaneous decoder that was developed in a couple of years back, okay, in the one-shot regime. Okay, So reliability is not a problem. We can get this pentagonal rate region. But what about the privacy? So unfortunately, the privacy is a little more difficult. So ideally, we need a simultaneous covering lemma, like the simultaneous decoder. So this is what we mean by the multi-terminal simultaneous version of the covering lemma to guarantee joint secrecy of Alice and Bob. So this directly leads to the famous simultaneous smoothing conjecture. I mean, especially troubling for us in the beyond IID community. Okay, so we would like to prove a covering lemma of this form. So, so the idea here is now, of course, there are two senders, Alice and Bob, and we'll do the same strategy, but so for each message pair m comma n, we'll have a block. And to index code words within the block, it's a two-dimensional block, so we'll require two indices k and l. And now, of course, Alice has encoded k into the xk in the input code word symbol, similarly for Bob YL. So what we want is that the average within the two-dimensional block, okay, this average where k and l vary independently should be close to the marginal state on Eve. Okay, and the expectation is taken over the random choice of code words within the block. So ideally, we'd like to prove a result of this form if log k, okay, so k is the exponent. So if k is larger than the max mutual information from x to Eve, L should be larger than the max mutual information from y to Eve, and the sum rate k plus L should be larger than the mutual information, max mutual information between joint xy to Eve. So this one is true in the classical. So this follows from the tripartite convex split lemma of Anshul, Jain, and Varsi. Okay. So the convex split lemma has a slightly different looking statement, but it can be repackaged and it's equivalent to a statement of this kind, at least in the classical case. And we would like to prove the appropriate CQ version, which is stated out. Unfortunately, the tripartite convex split lemma is proved for the non-smooth information quantities. Okay, so we do not have a statement where all the three quantities are simultaneously smoothed. So this is the simultaneous smoothing conjecture. At most, we can smooth one of these quantities, but not the other two. So that's the state of the art. Now, ideally, we would like to prove a secrecy region like this. So in the asymptotic IID regime, it should look like this. Okay? So the two corner points would be like this: the mutual information from X to Eve and the mutual information from Y to Eve with side information X, and similarly out here. So this will be the conjecture for the IID version. So you can state as analogous conjecture for the one-shot version. Yeah. Now, okay. So, but we cannot quite prove that. So the main contribution of this work is that under the same setup as the ideal lemma, we can guarantee this secrecy condition, okay, for the corner points. We don't know how to do time sharing, but we can guarantee it for the two corner points in the one-shot version. So these are the corresponding corner points out here, with I replaced by I max. And we can, so what do you get for the asymptotic IID regime? So we can get the corner points for reliability, we can get the corner points for secrecy, and then we subtract the privacy part from the secrecy to get these corner points, and then we can time share between them. So we do get this pentagonal rate region that we want. But what happens for one shot when you don't have IID? So, okay, so the issue here is time sharing can no longer be done. But the solution is we can bring in another tool from our arsenal. So we can do rate splitting. So we can split Alice into two virtual senders, Alice 1 and Alice 2. So this was addressed in actually a talk that was given by Sayantan in Beyond IID last year. So the rate splitting was a technique originally introduced in classical IID, but it turns out that it can be lifted to the one-shot quantum setting. So we can use rate splitting and successive cancellation to get some intermediate points. But unfortunately, I mean, we would like to get this pentagonal region, but we cannot guarantee that we get all of it. And part of the reason is that in the one-shot case, if you do rate splitting, some rates can become negative. Another part is we don't have a chain rule for Imax with exact equality. So we can get some kinks like this. So we are within the ideal pentagonal conjecture region, but we can get kinks like this. Okay, but at most one such kink we can prove. So this is what the region looks like. These are the corresponding corner points, and that's it. That's all I have for today. Thank you for your attention, and yeah, questions.
Thanks a lot, Pranab, for this nice talk. Yeah, we have questions. I don't see any typed, I think, but anyone, please.
Let's stop the sharing.
It's okay. Maybe you leave it for now, so whatever you prefer.
Can you hear me?
Hello.
Yes, we can hear you. Please.
Yeah.
So just one question to Pranab. Thanks for the talk. So the kink that you mentioned, that is through the joint smoothing, right? You're trying to do joint smoothing when you talk about this missing, the missing piece here.
Well, the kink comes for two reasons. So remember, we have to do rate splitting. So rate splitting means we will break up Alice into two virtual senders, Alice 1 and Alice 2. And what will be the successive cancellation encoding and decoding strategy? So Charlie will first decode Alice 1, treating Alice 2 and Bob as noise. Then she will decode Bob, treating Alice 1 as side information and Alice 2 as noise. Then she will finally decode Alice 2, treating Alice 1 and Bob as side information. Okay, so that is the successive cancellation order. So now it turns out that if you split Alice into Alice 1 and Alice 2, so we have to split the mutual informations, this IH and IMAX, both IH and IMAX. Okay. Now it turns out that in the one-shot case, one of these splits that, one of these rates that is coming from this rate splitting map can turn out to be, well, actually IH can never be negative, sorry. So IMAX can become negative. So that's reason one of this things. So remember, the Shannon mutual information is never negative.
Sorry for interrupting. I just joined. Actually, the difference can turn out to be negative. Individually, they can't. The difference can turn out to be.
Oh, okay. So thanks for the clarification. So this difference can turn out to be negative.
I get that. My question is slightly different. So all this is in the one-shot setting, and what if I understand right is if this is the IID setting, and you do a corner point time sharing, then you achieve the kink is not there.
Yeah. IID quantum also there is no kink because we do the corner points. So we don't need the rate splitting. We can get corner points by successive cancellation for reliability, successive cancellation for privacy. Okay, and then just take the difference. So I can get this corner point. I can get this corner point. I'll do time sharing. So time sharing, of course, gives me any rate point out here, and you can easily prove both reliability and privacy for any point out here. So that's not so difficult.
Okay. Thank you.
Thanks. Do we have any more questions?
Yeah, it's not a question. I just want to thank Pranab for giving the talk at such a brief year, because I actually hurt myself and I was supposed to give the talk, but anyway, thanks Pranab, and thanks the organizers for allowing this at such short notice.
I hope we'll be better soon. Yes. Sorry to hear.
Okay. Yeah.
Okay, so Pranab, can you put on the simultaneous smoothing conjecture slide maybe quickly?
This one, huh?
Yes. So here in the conjecture, the C system actually doesn't appear, right? So it's just like classical quantum state.
So the covering lemma is stated for a classical quantum state. It's the X and Y are classical, E is quantum. So one can, if you drop the smoothed quantities, then we can prove this for IMAX, not I epsilon for IMAX, from the tripartite convex split lemma. So the tripartite convex split lemma says the following, like it says that take 2 to the k independent copies of X. So the tripartite convex split lemma holds in the fully quantum case also. Okay. So informally, it just says that take 2 to the k independent copies of X from the marginal quantum state. Take 2 to the L independent copies of Y from the marginal quantum state on Y. And then take 1 copy of E from the marginal quantum state on E. So rho XY is some joint quantum state. So this is a product of marginals on 2 to the k X's, 2 to the L Y's, and 1 E. So the tripartite convex split lemma says that this state is very close to the following state. So choose an index k, comma L uniformly at random. Okay, so k is uniformly from 1 to 2 to the k, L is uniformly from 1 to 2 to the k. So choose this k, comma L uniformly at random. And now let me put a joint state on the kth copy of X, Lth copy of Y, and the E register. So make them joint according to rho XYE. And keep the others as it is. It's a product and with each other and all, with the margins. Okay. So so I picked a random k, comma L and entangled it the way I desire with E. Okay, and now this k, comma L I randomize over like all possibilities uniformly. Okay. So that's the word convex. So I'm entangling a k, comma L, and then I'm taking a uniform convex combination of it. So this is the right hand state. So the right hand state is very close to the left hand state, which are everything in tensor product. So now if I convert, now if I specialize to X and Y classical, okay, then the convex split statement is equivalent to this covering statement.
Okay, yes.
Okay, and this expectation is taken over the probability distributions, the IID distributions of X and Y, Y out here. Okay, not written here. Yeah. So so after we put in the expectation, we get this. So I would like to think of it as covering in expectation, because the expectation is over the choice of the classical symbols. So one can also ask whether for most settings of the classical symbols, these two, this L1 distance is small or not. So that would be covering in concentration. So the Elsewhere-Winter type of covering lemma is a covering in concentration lemma. Turns out that for our purposes, or even the older wiretap purposes, we don't need covering in concentration. That is too strong an ask. Okay, all we need is covering in expectation.
No, but actually, so recently we did notice that with this sort of statements, one can convert into a concentration type of statement with some very easy tweaks using McDiarmid's inequality or something like that. So convex split is very powerful. That's the sort of message that we want to give.
Yeah. So I mean, what we observed is that if you have closeness in expectation, then we can actually get a closeness concentration, and we can beat what Elsewhere-Winter did. So Elsewhere-Winter's concentration had a dimension factor multiplying the exponent. Okay, so we can avoid that multiplication factor, and the way to prove it is just apply McDiarmid's method of bounded differences to the quantity inside. So all it says is that let's say I change just one point out here. That means fix a k, comma L, and let's say I change the state out only for that k, comma L. So how much can the L1 distance change? It can change by at most 1 over 2 to the k times 2 to the L. So if the maximum change for each perturbation is small, so that's the ideal setting for using the method of bounded differences, so use a version of this concentration by McDiarmid, but who derived it in turn from Azuma's inequality for martingales. So we don't actually need the operator chain of bound to even get a result in concentration, and we can save a dimension factor also in the bound.
That is very nice.
We don't need that for this purpose.
That is actually very good. That is actually very nice.
I agree. Yeah, so I would love to chat more, but I think we have to stop here. We're already a bit over time. But yeah, thanks again, Pranab. Thanks again, all the speakers of the session. And I think we will reconvene in like 20 minutes approximately. Yeah, thanks, guys.